Hello everyone, my name is Yu Wang and this is my teammate Yu Zhang. We have developed a network restore system for people to have internet access when they are physically located in a crowded space. Consider yourself going to a music festival and there are thousands and thousands of people in the live house. People tend to take out their phones and take a picture or two, or maybe record a small video, and they want to send that to their friends or family to have them enjoy the moments with them. But they can't do that because interference is an issue. Everybody is trying to establish a connection to the nearest cell tower and using the similar bandwidth, similar channel to send data. And that causes interference. And that makes no one have reliable communication. Why we need a network restore system? Because there are many messages considered time sensitive. If you want to have an Uber ride right after you finish the festival, you might want to order one in advance. And the weather condition is something you also want to know. If there's a heavy rain outside, you want to text your friends or family to pick you up. And the friends or family needs to know when and where to pick you up. Last but not least, just like what I said, you might just want to send a picture to your friends, have them enjoy the moment with you, and show them how much you like the music.
There are various ways to network congestion, such as restructuring the network. We can upgrading hardware, such as some basic network equipment like routers and switches to make the communication network more efficient. Also, some communication protocols like Cisco CD using wireless communication, it can avoid collisions in the carrier. And the framework such as QoS can ensure the priority transmission of some critical data in the network. In this project, we use Bluetooth broadcasting participant in the network, which means it will not bring in more infrastructures into the system.
That's why we proposed and developed the next generation network restore system. It is essentially a collaborative network, but only smarter compared with the conventional ones. We will dive into detail later, but now we have to understand two key concepts. The first one is called broadcaster, and the other one called mailman. The broadcaster will use its BLE module on the commercialized cell phone to send message to its nearby mailman, and each broadcaster will have 1 megabit per second data rate. For the mailman, it will use 5G network and BLE module together to support the network. What mailman would do, the mailman will pack nearby and its own message together, put everything in a packet, and send it through to the cell tower. Each mailman will have a 10 megabits per second data rate. So why we call it a smart collaborative network? It is because the network doesn't require prior role assignment. Each node will not know its role assignment until they join the network, meaning the role assignments is on the fly. And people will have a role switching periodically. Consider a case that 8 of them in the concert will not have reliable communication, and they all join the network, and by default, everyone is a broadcaster. They will use the BLE module to communicate with each other to see if there is a mailman nearby, and they will quickly know that no such mailman exists for now. How the system going to pick the first mailman is depend on the time you join the network. Let's say if the center person joined the network first, and it is likely to become the first mailman. The mailman will use the BLE module to broadcast out and let all other surrounding broadcaster know, hey, there's a mailman available. If you want to send out some data, let me know. Whenever a broadcaster has some data you want to send out, they will first push the data to the mailman using the BLE module, and the mailman will pack everything together and send it to the cell tower using its own 5G network. This is actually the core concept of our network restore system. We want to limit the number of people to have internet access and forcing rest of them using BLE to avoid interference.
Using Bluetooth, both Bluetooth and 5G at the same time has high power consumption. So switching roles it became very important for balancing the consumption of energy and flow, data flow among all of the nodes. We test 3 models in the simulation, and randomly switching the nodes will tend to concentrate more flows in some typical nodes. These critical nodes might cause congestion in the network. The second one, we switch with a nearby broadcaster. The node in a small group switch the roles with each other, and it can maintain the geometric distribution stable in this small group. The third one we switch depends on node lifespan. The system will select a node with smaller total flow volume to be the mailman, and it can reduce the write-ins to a certain degree.
So we also develop a simulation to tell how well the system gonna perform. The green line shows number of broadcaster, orange line shows number of people who haven't joined the group yet, and the blue line shows the number of mailmen. Regardless of some fluctuation on the blue line, that is because the switching policy plays a role here. We only need 45 to 50 mailmen to support a 900 people simulation. In this page, we have cross-compared all 3 performance graphs under 3 different switching policy. And we can see all of them share similar feature, meaning we only need, regardless of the switching policy, we only need 45 to 50 in average of mailmen to support this 900 participant simulation.
We use 30 by 30 heat map to represent the amount of the data submitted by every node during the whole simulation. And the deeper red indicate that these nodes transmitting more bytes. Using different switching roles, the balance of the balance of the flow had improved, and this balance also make the data rate reach a higher level.
This is how the data rate gonna look like by using the second and the third switching policy. Although both policy can result in a fairly high data rate, but the third policy is fairly more stable. You can see the fluctuation on the right side of the graph is more stable compared with the left side of the graph. This is the result we get from the 900 participant simulation. We only need, in average, 47 mailmen to support this 900 participant simulation. And the simulation result in 47 megabits per second data rate, meaning 45,000 messages will send out per second. And that averaged down to 50.2 messages per person per second for all 900 participants.
Why this new system is better? It's because that we use Bluetooth broadcasting to participate in the network, which means they will not bring in new infrastructures into the system. Also, it makes the network more cost-effective and broaden its range of application scenarios. Also, compared with some classic network, this system does not assign the role of the nodes during the initialization, which means during the switching iterations, every node might change into mailman or broadcaster. This dynamic switching ensure a balance in both energy consumption and flow distribution. As more and more nodes add into the system, the switching rules become more effective, and so this dynamic mechanism eventually could maintain stable even some of the node fail in the system. These networks still need a lot of improvements in the network topology. There are actually some of the nodes actually stay in a very isolated position, which might lead to a very extreme data flow situation. And also broadcasting lack of the point-to-point feedback. So we think about build and resend mechanism and use a more flexible delay control mechanism to do on the AP node.
Thank you for listening to our presentation. If you have any question, please leave on comment. Thank you.